Hello, my name is Thomas. I'm a lecturer in applied mathematics here at the University of Leeds. And in this podcast, I want to tell you something about a very simple mechanical model which gives rise to some interesting mathematics. The model is the motion of a particle that is attached to a spring, and we will see that it leads to harmonic motion. So here we have a particle that is attached to a spring, and the spring is attached itself to a wall. Now, if there's no motion, if the particle is at rest, then the spring will have a certain length, which I call L, and this is called the equilibrium position of the particle. And what I want to do now is I want to push the particle to a different position, and then I want to release it, and I want to find out what happens with the particle afterwards. So if I push the particle, this means I'm applying a force, which I will call F, to the particle. And in this instant, I'm pushing it to the left to a new position. And the spring will then have a new length, L plus x, where in this case, x would be negative. So x is a negative number. The question, like I just said, is what happens when I remove this force? Well, the expectation is that the particle will move back to its equilibrium position. And we will want to analyze this motion of the particle after the force F is removed. And there are many ways you can analyze these problems with. You can use energy methods. What I want to do is I want to use Newton's laws. They will give us a differential equation. The solution of the differential equation will tell us how the particle moves. For Newton's laws, I need to investigate what are the forces acting on the particle. And since I have a spring, there is a very famous law called Hooke's law, which has been derived by the English physicist and experimentalist Robert Hooke, who lived at the same time as Newton. And this law tells us the following. If I want to push the particle only a little bit, then I will only move it slightly. If I push it a bit harder, then I will move it further. And in fact, the displacement of the particle is exactly proportional to the force I'm exerting on the particle. I can write this as a mathematical formula, and this is the mathematical version of Hooke's law. F, the force that is exerted onto the particle, is a number k times the displacement from the equilibrium position. This number k only depends on the material properties of the spring, and therefore it is called the spring constant. And now I want to use Newton's laws. These laws will give me an equation for the motion of the particle, and this equation is commonly called the equation of motion. First of all, I need to figure out what forces are actually acting on the particle now. Whilst I'm pushing, I've got the force F. And by Newton's third law, I've got an equal and opposite reaction force, which I call Fr. It has the same magnitude, but just the opposite direction, so this is minus k times x. This force is shown as the red arrow here. And now I want to make a very important assumption. I want to assume that this force, once I removed F, is really the only force acting on P. So this means in particular that I don't have any friction between this particle and the ground, or I don't have any air resistance and things like this. So this will be a very simple mechanical model, but we will see that the mathematics will be difficult enough for us. And now I want to use Newton's second law. Newton's second law tells us that the force is proportional to the acceleration of a particle. F is m times a, and a, as usual, denotes the acceleration of a particle. I need to express the acceleration in mathematical terms. I want to have a formula. Well, z is the position of the particle. I used this before. And you probably know that the velocity of a particle at time t is the first derivative of its position. The acceleration, on the other hand, is the first derivative of the velocity. And this means the acceleration is just the second derivative of the position. A is d squared z dt squared. However, there's a slight problem. I've expressed the force in terms of x. I expressed the acceleration in terms of z. That's not good. I only want to use one variable. So I have to rewrite either one. And I chose to rewrite the acceleration in terms of x. This is very simple because we have a very simple formula that relates z to x. Z is just the equilibrium position plus the displacement. Now we differentiate this equation. If z is L plus x, where L is a constant, then the time derivative dz dt is equal to the time derivative dx dt, and in the same way, the second derivative of z is equal to the second derivative of x. And that's all I need to write down Newton's second law. F is m times a. Remember, the only force I have acting on my particle, that's the assumption that I don't have any friction, is this reaction force Fr. Okay, so m times a is Fr. I know what Fr is, that's just minus k times x. I know what the acceleration is, there was a second time derivative of x, and I multiply this. Now to make it look a bit nicer, I just bring this over to the other side. So I have an equation m times the second derivative of x plus k times x is equal to 0. Now if I find a solution of this equation, then this will show me how my particle moves for positive times. If I want to solve an equation, I first have to figure out what type of equation it is. And we have to look at this quite carefully because it's a fairly difficult equation to solve. You see, the position x, or the displacement x, will obviously change in time. So x is really a function of t. That's why we've got a time derivative here. So we've got an equation, that relates the second time derivative of a function x of t to x of t itself. Now you know that this is called a differential equation. In fact, here the second derivative appears, so this is a second order differential equation. In general, these equations are quite difficult to solve. However, this type is quite easy because the derivative and x itself only appear in what is called a linear term. We have the derivative multiplied by some number, and we have x multiplied by some number, and then we have these two terms added together. So this is a linear second order differential equation, and thankfully there is a method to solve this type of equation. So I've just put this here again. The equation of motion for the particle on a spring is a linear second order differential equation. Now I don't want to solve this equation in general. What I want to do next is I rather want to look at one more specific example and talk you through the method for how to solve such an equation.